Okay, in this video we're talking about acceleration, acceleration in straight lines and also centripetal acceleration, and we'll discuss that here in a little bit. I think most of the time whenever we think about acceleration, we have this idea that acceleration is just moving, whenever we start moving faster, and that is just going in the forward direction. So I want to kind of readjust what you think of acceleration and readjust your definition of acceleration. So if we look, I think it's important to define it first. So if we look at acceleration, it's simply the rate of change of velocity. So these are kind of the key words here. The rate at which we change velocity is the definition. So whenever we think about acceleration, I want you to think about what this actually means when I give you guys some examples here. I think it's also important to discuss the differences between kind of speed, velocity, and acceleration, because sometimes we get velocity and acceleration kind of mixed up a little bit, like in the bungee example that I gave you guys, the guy bungee jumping. Speed, if we look at it, we got to look at whether it's a scalar or vector again. So speed is a scalar quantity, so that just means that we look at the quantity, right, or the magnitude in that case. So it could be like 23 meters per second. Velocity, on the other hand, velocity is going to be a vector quantity. So we not only have to know the magnitude or how much, right, like 23 meters per second, but we also need to know direction. So we could say it's going west. Acceleration, because acceleration is the rate of change of velocity, it is also a vector quantity because we need to know direction. So if we change anything about velocity, then we are accelerating. So that would be like 23 meters per second every second. So we could write it like that for our units, or we could do meters per second squared for our units. So every second we are changing our velocity by 23 meters per second. So if we were to, let's kind of do some examples here. If we were to change, if we were to go faster and faster, if we increased our speed, so these are, here, let's just write it like this, 3 ways that we can change, 3 ways to change acceleration. Or acceleration. Can't spell right now. So 3 ways to change acceleration if we increased velocity. So this is kind of the main way we think of acceleration. If we increased velocity, would we be changing acceleration? Yes, because we are changing the velocity at that point. If we decrease, so if we started slowing down, if we were driving in a car and we slowed down, would that be us accelerating? Yes, it would. Because again, look at the definition. It's the rate of change of velocity. It doesn't matter if you're speeding up or slowing down, you're still accelerating. Sometimes we call that deceleration. So also the third way is if we, and this is kind of the way, one of the ways that we don't really think about, are we accelerating, if we change direction. So because we have to know direction in velocity, then if you change that direction, so if you start driving around a corner, are you accelerating? Even if you're going at constant speed or constant velocity, so even if you're going at constant velocity at one velocity around that corner, because you're changing direction, you're also accelerating. So those are the 3 ways we accelerate. So if we look at our definition, we can kind of figure out what our equation is for acceleration. Our equation is A for acceleration is equal to our change. So remember, the delta means change in something. So the change in velocity over the change in time. So the rate of change of velocity. So how much did velocity change over time? But this is our equation that we're going to use to solve some of the problems. And you may want to write those in your notes. You may also want to have the 3 ways that we can accelerate. So let's look at centripetal motion. So centripetal, if we look at that word, it kind of tells us what it means here. So centri meaning center, and then pedal meaning seeking. So it's center seeking motion. Kind of makes sense because we're talking about motion in a circle. So if you guys, during our activity, we walked in a circle. If you're walking in a circle, so let's just look at you at one point during that circle, which way were you facing? You'd be facing in this direction. So if you look at it, you have to constantly change your direction, and you have to constantly use a force to change that direction to keep going around in a circle. Now let's go, say that's at 1 second, let's go another 3 seconds. Where were you at? You maybe right here. Now you're facing in this direction. Go another 3 seconds, maybe you're right here, and now you're facing in this direction. So you're constantly having to change which way you're facing. And the way you're going to do that, which way are your forces being applied? If you think about it, what are you doing to stay in that circle? You're going to be pushing down, applying a force with your foot on the ground. And which direction are you going to be applying it? Your foot is going to be applying the force in that direction. Now the floor, you may not think of this, the floor, which way is it going to be applying a force? It's applying a force back in the opposite direction that you're applying that force. So that goes along with Newton's laws, which we haven't covered yet, but the floor is applying a force in this direction. So that's what's allowing you to keep going toward the center here. So whenever you're going in a circle, you're constantly moving toward that center, toward the center of that circle, keeping you going in that direction. Just to kind of give you some more examples of force and how our centripetal motion. Again, if we're constantly changing direction going in a circle, what are we also doing? We're constantly changing our acceleration. So anytime we have centripetal motion, we also have centripetal acceleration. Okay, so this example, we have a yo-yo here. So if you guys have ever had a yo-yo, you have a string out here, and maybe you are just taking it, if you don't know what you're doing with the yo-yo, kind of like me, you'd probably just end up just swinging it around in a circle. So if you did that, if we were swinging the yo-yo around in a circle here, it's kind of a bad circle, but where would that force be in order to keep it going around in that circle? It would be this tension on the string, and so the tension on the string is pulling that yo-yo toward the center in that case. So that would be one example. Another example might be if you were satellites that are orbiting around the Earth. So this is the Earth. I'll try to draw a satellite here. I don't know how good of an artist I am, but so this would be the satellite, and it's just orbiting around the Earth. So what kind of force is keeping that satellite orbiting around the Earth in this direction? That would be the force of gravity. So the force of gravity from the Earth is pulling it toward the center of the Earth the entire time. Even though it's moving in this direction, it's constantly has this pulling force, and that's what keeps us all on the surface of Earth is gravity. So that's another example of centripetal motion. The last one here would be like a car. So if you're driving your car on a racetrack, and also if you're going at constant speed, remember, another example of that, and you're changing direction, then would you be changing your acceleration? Yes, you would, but this would be centripetal acceleration. So it might be a little less intuitive, like what is keeping this car from just keep going straight off the track? What is allowing it to turn the wheels? It would be the friction between those wheels in that direction toward the center. So that would be centripetal motion. Okay, so doing some practice problems here real quick using our formula that we figured out. And please don't ask me where I got these problems. You'll see they're kind of crazy, but so the tune train is traveling at a speed of 10 meters per second at the top of the hill. 5 seconds later, it reaches the bottom of the hill, moving 30 meters per second. So here is a velocity, here is a velocity, and it takes 5 seconds to get there. So there's our time. What is the rate of acceleration of the tune train? So we just got to plug these numbers into our formula here. So it starts out, our initial velocity would be 10, right? So that would go right here. Our final would be 30. So we have 30 minus 10 meters per second. And then our time, it would be 5 seconds. So what is our initial time? 0 minus 5. So 5 minus 0 would just give us 5. And then we would have 20 for our meters per second. So 20 divided by 5 would give us 4 meters per second squared. So how do we get our units on this one? Well, if you think about it, up here we have meters per second, right? Because these are our velocities. Down here we have time, which is seconds. So meters per second divided by our time. So we put another slash in there and we get another S. So really it would be like this: meters per second divided by our time would give us divided by another second. But we can just write that as meters per second squared. Okay, so I want you guys to, I'm going to give you guys a couple practice problems. Right here you can see Pete the Penguin, Monster Mike's truck. I want you guys to solve those. Like I said, don't ask me where I got these problems. I want you guys to solve those using the formulas. And one more thing, if you guys like using this to figure out what you're going to be doing with it, this example, if you're going to write these in your notes, it would look kind of like the velocity problem, but you're going to have acceleration down here, velocity up top, and then time on the side. All right, good luck, and hopefully this was helpful. I'll see you guys in class.